which I am giving you is not in the syllabus of 2020-21, but here I am going to discuss every topic for your other session as well as competitive exams. Now, principle of superposition of forces between multiple charges. The mutual electric force between two charges is given by Coulomb's law. How to calculate the force on a charge? Well, there are not one but several charges around. Consider a system of n stationary charges Q1, Q2, Q3, so on till Qn in vacuum. What is the force on Q1 due to Q2, Q3, so on Qn? Coulomb's law is not enough to answer the questions. Recall that forces of mechanical origin, and according to the parallelogram law of addition, is the same true for forces of electrostatic origin. Now I am giving a figure to understand. It is verified that force on any charge due to number of other charges is the vector sum of all the forces on that charge due to the other charges taken one at a time. The individual forces are unaffected due to presence of other charges. This is termed as the principle of superposition. To better understand the concept, consider a system of three charges Q1, Q2 and Q3 as shown in the figure above. The force on one charge, say Q1, due to two other charges Q2, Q3 can therefore be obtained by performing a vector addition of the forces. Two other charges. Thus, if the force on Q1 due to Q2 is denoted by capital F underneath 1, 2, comma capital F underneath 1, 2 is given by equation 3, even though other charges are present. Thus, F12 equals to 1 by 4 pi epsilon naught Q1 Q2 by R12 square R1 into R12 unit vector. In the same way, the force Q1 due to Q3 denoted by F13 is given by F13 equals to 1 by 4 pi epsilon naught Q1 Q3 divided by R13 below that square and R13 unit vector multiplied. Here is the figure of system of multiple charges. Which again is the Coulomb force on Q1 due to Q3 even though other charge Q2 is present. Thus the total force F1 on Q1 due to the two charges Q2 and Q3 is given as F1 equals to F12 plus F13, that is equals to 1 by 4 pi epsilon naught Q1 Q2 divided by R12 square into multiplied by R12 unit vector plus 1 by 4 pi epsilon Q1 Q3 divided by R13 square multiplied by R13 unit vector. The above calculation of force can be generated to a system of charges more than 3 as shown in B. The principle of superposition says that in a system of charge Q1, Q2 and so on to Qn, the force on Q1 due to Q2 is the same as given by Coulomb's law, that is, it is unaffected by the presence of the other charges Q3, Q4, so on till Qn. The total force F1 on the charge Q1 due to all other charges is then given by the vector sum of the forces F12, F13, so on till F1n. That is F1 equals to F12 plus F13 plus so on till plus F1n equals to 1 by 4 by epsilon naught in bracket Q1 Q2 divided by R12 square into R12 unit vector plus Q1 Q3 divided by R13 square multiplied by R13 unit vector plus so on till Q1 Qn divided by R1 square multiplied by R1n unit vector, so equal to Q1 4 pi epsilon naught integrated I equals to 2 and Qi by R1I square multiplied by R1I unit vector. The vector sum is obtained as usual by the parallelogram law of addition of vectors. All of electrostatic is basically a consequence of Coulomb's law and the superposition principle. Now problem 1. Consider three charges Q1, Q2, Q3 each equal to Q at the vertices of an equilateral triangle of side L. What is the force on a charge capital Q with the same sign as small q placed at the centroid of the triangle as shown in the figure? Listen to this problem. In the given equilateral triangle ABC of sides of length L, if we draw a perpendicular AD to the side BC, AD equals to AC cos 30 degree equals to root 3 by 2 L, and the distance AO of the centroid O from A is 2 by 3 AD equals to 1 by 3 L. By symmetry, AO equals to BO equals to CO. Thus, force F1 on Q due to charge Q, small q at A equals to 3 divided by 4 pi epsilon naught capital Q into small q divided by L square along AO. Force F2 on capital Q due to charge small q at B equals to 3 by 4 pi epsilon naught capital Q into Q divided by L square along BO. Force F3 on Q due to charge Q at C equals to 3 by 4 pi epsilon naught capital Q into small q divided by L square along CO. The resultant of forces F2 and F3 is 3 by 4 pi epsilon naught multiplied by capital Q into small q divided by L square along OA by the parallelogram law. Therefore, the total force on capital Q equals to 3 by 4 pi epsilon naught capital Q into small q divided by L square multiplied by R vector minus R vector, that becomes 0, where R is the unit vector along OA. It is clear also by symmetry that the three forces will sum to 0. Suppose that the resultant force was non-zero but its some direction. Consider what would happen if the system was rotated through 60 degree about O. Another problem, number 2. Consider the charges Q1 and minus Q placed at the vertices of an equilateral triangle as shown in the figure. What is the force on each charge? Solution of the problem. The forces acting on charge small q at capital A due to charge Q at capital B and minus Q at capital C are F12 along BA and F13 along BA and F13 along FC respectively, as shown in figure. By the parallelogram law, the total force capital F1 on the charge small q at A is given by F1 equals to F1 is capital F equals to capital F R1 is unit vector, where R1 is a unit vector along BC. The force of attraction or repulsion for each pair of charges has the same magnitude. Capital F equals to Q square divided by 4 pi epsilon naught L square. The total force F2 on charge Q at B is thus F2 equals to capital F2 equals to capital F into R2 unit vector, where R2 is a unit vector along AC. Similarly, the total force on charge minus Q at C is F3 equal to root 3 into capital F into N unit vector, where N is the unit vector along the direction bisecting the angle BCA. It is intersecting to see that the sum of the forces on the three charges is 0, that is F1 F2 plus F3 equals to 0. The result is not at all surprising. It follows straight from the fact that Coulomb's law is consistent with Newton's third law. The proof is left to you as an exercise.